today's lesson we'll start off our last unit, which is on gases and atmospheric chemistry. So to introduce the unit, we first need to talk about how gases behave with the kinetic molecular theory. Then we'll look at gas pressure and temperature, and then we'll learn about some gas laws and how to do some calculations with them. So the first thing that we're going to do is look at states of matter and motion, and this is part of the kinetic molecular theory. And it's important to understand how gases behave differently from other states. So if you have a solid, we know solids, their shape and volume don't change. So we say they have fixed shapes and fixed volumes. In terms of motion, they actually do have a type of motion. We don't see it, but the molecules vibrate on a really small scale. So they're all attracted to one another or bonded, and they just kind of vibrate gently in place. But this type of motion we say is restricted because it's not changing the shape or volume of the substance. What happens with liquids? What makes them a little bit different than solids? Well, we know their volumes don't change, so you still see that fixed volume occurring, but their shapes are not consistent. The shape will take place of whatever the container that that liquid is in. So you put water in a glass, it takes the shape of the glass. You let the water spill out on the counter, it's going to go all flat and spread all around the counter. So the shape is not consistent. In terms of motion, they have vibrational motion like solids, but because their shape changes is inconsistent, they have a second type of motion which we call rotational. So those molecules can change their position as they're in motion. When we get to gases, you'll notice they're very different, and you know they behave differently. They don't have a consistent shape or a consistent volume. They'll keep spreading to fill whatever volume container that they're in, and their shape will take on whatever that container is. Because their shape and volume are inconsistent, they have three types of motion. They have the same rotational and vibrational motion, as were previously mentioned, but they have an additional type of motion, and this is what makes them unique. It's called translational motion, which means they're pretty much free to move wherever they want. They've got lots of energy, they will keep moving and expanding to fill whatever container that they're in, and so on. A good way of thinking of this is if you have something that's been turned into a gas, maybe like a aerosol spray, air freshener, even some perfumes or deodorants. If you spray it in one part of the room, that gas will keep spreading and spreading until it fills up the entire room. So you might not smell it right away if someone were to spray one of those things in one corner of the room, but over time it would keep spreading and you would smell it throughout the room. Or if you are at school, in the hallway at your locker, someone down the way sprays some deodorant and it makes it scent all the way down the hallway at some point. So those are some good examples to think about gases and their motion and their movement. So because gases can be unpredictable and they have lots of types of motion, when we look at the kinetic molecular theory for describing gases, we're going to make some assumptions. And since we're making some assumptions, we're calling these types of gases ideal gases. They behave this way all the time, so we don't have to worry about any inconsistencies when we're talking about gases, their behavior, and even with calculations. In reality, there are some things to consider. But if we assume we have a gas that's behaving perfectly without any errors, without any anomalies, anything like that, you're going to see these assumptions take place. So what are they? First one, the volume of a gas is negligible. A gas will expand to fill its container. So imagine you have a flask. It has a stopper on the top and it can hold 100 milliliters of gas. So 100 milliliters of gas is in that flask. Is it truly 100 milliliters? No, because the gas molecules themselves occupy some space. So if you wanted the exact volume of gas that was in that flask, you would take 100 milliliters and subtract the volume of the molecules. But molecules are really tiny, and the amount of space and volume they occupy is very, very small. So we can basically ignore that or say that it's negligible. It's going to be pretty close to the volume of that container, or in our example, 100 milliliters. Next, we're going to say there's no intermolecular forces between molecules. Remember, intermolecular forces we talked about last unit, hydrogen bonding with water, and there are other types like dipole-dipole and London forces that are between different gases. So we're going to assume that there's no forces attracting the gas molecules. They move around on their own. They're not affected by the other molecules that are there. Next, gas molecules move randomly, which means they have high translational motion, moving in all directions and in straight lines. So to assume that gases are moving around all the time, we have to assume they have lots of translational motion. But the thing that's important to note here, that while it is random motion, we want to consider they can move in all directions in 3D, but they have to move in straight lines. So we're going to assume they're not curving or being pulled one way or another, anything like that. They have to travel in straight lines. If we do this, it helps us calculate pressure. When we talk about pressure in a few minutes, pressure of a gas is directly related to how much the gas molecules are moving. And if we make this assumption, pressure calculations are very straightforward. Let's take a look at a few more parts of the kinetic molecular theory. Part 4, the collisions between the molecules and the container are what we call perfectly elastic collisions. Now, if you're in physics, you might be familiar with this term. If you see an elastic collision, that means when the two objects collide, you don't lose energy. So molecules are definitely going to collide with one another as they randomly move around, but we're going to assume that they keep all the energy that they have. We know that they might transfer or gain a bit of energy depending on what's going on, but the amount is so small that we're just going to assume that no energy is lost. And finally, last point of our kinetic molecular theory has to do with temperature. So when we talk about temperature, we say that it has a direct relationship with what we call the average kinetic energy of molecules. Kinetic means motion. So here, the kinetic energy is a type of energy associated with motion, and they're directly related to one another. So that means as one goes up, the other one goes up, and as one goes down, the other one goes down. They behave the same. So if temperature is increased, you'll find that the kinetic energy of your sample increases as well. If the temperature goes down, the kinetic energy of the gases will go down, and that can have direct effects on things like pressure and volume and so on. So those are the 5 key points of the kinetic molecular theory, and we're going to assume that we're following these points when we get into our gas law calculations throughout the unit. Before we can start using some of the gas laws, we have to first learn about gas pressure. So first, what does the word pressure mean? It's how much force is applied on an object, but specifically it's looking at a type of unit of surface area. There's many different types of units of pressure. These are some common ones used in science. ATM, or atmosphere. mmHg, it stands for millimeters of mercury. This one isn't used as much before, as much as it used to be. Before, it was used in barometers that had mercury in them, but we know mercury isn't safe anymore, so these aren't typically commercially available. You can still get them for lab purposes, but commercially they don't sell the mercury anymore because it's not good for you. There are a couple other units. Torr, it's after a scientist named Torricelli who claimed that unit of pressure in the 1600s. And then the Pascal is one that's very common. It's our SI unit for pressure. In terms of places where you'll see pressure, Pascal, or often on the news when they're talking about weather, you might hear kilopascals, just the same prefix like kilogram. This is kilopascal. You might see that one very commonly reported. There are other types of pressure you might see in common places, like on tires. They use PSI, pounds per square inch, but that's not with our metric system. That's with the empirical system. So in science, we tend not to use that, but you might find it on things like tires. So in terms of pressure, they are all related to one another, and you will run into problems where you will have to use different pressures. So how can we convert between one another? So what we do is we're going to look at pressure at a set condition. This is called STP. STP stands for standard atmospheric temperature and pressure. What are these conditions referring to? At 0 degrees Celsius and at sea level, because if we're not at sea level, that also affects pressure. It'll change. You'll notice that these four units are related to one another with this conversion or this relationship. 760 millimeters of mercury is equal to 760 torr. So you'll notice these two both have the same scale, 1-to-1 scale, but those are equal to 1 atmosphere or 101.3 kilopascals. So think of these like a conversion or a ratio, 760 millimeters of mercury to 760 torr to 1 atmosphere or to 101.3 kilopascals. Any one of those can be used to do converting. So let's try out some converting problems with pressure. So what if we wanted to convert 98 kilopascals to torr? Well, we're going to use our unit analysis method we've been working with throughout the course. So I take my unknown, which is torr, and I'm going to start with my given value here, which is 98. And I'm going to multiply it by my conversion factor. Now, where am I going to get it? I'm going to get it from my relationship up here. So I need 101.3 kilopascals, and I need 760 torr. Those are the two measurements that are related to this question. What I'm trying to solve for, torr needs to go on the top, and what I'm trying to eliminate is going to go on the bottom, so I can cancel my kilopascals and kilopascals. Okay. Then you can see kilopascals will cancel, and you're left with torr. So now you can plug that in your calculator, 98 times 760 divided by 101.3, and then you're going to get 735.24 torr. And then, of course, since we're not doing anything else with this number, if you were just to do a conversion, you would round to significant digits. So this is 3 significant digits, so here we would need to round to 3. So why don't you try one out? Pause the video and see if you can do this conversion. 81 atmospheres converted to kilopascals. So pause the video, try it out, and we'll take a look at the answer. Okay, let's check how you did. So when you're setting up your calculation, you want to take your unknown again, 81, but this time we're going to use kilopascals and atmospheres. So the atmospheres will cancel, and you're left with kilopascals per unit. So 81 times 101.3 divided by 1. If we do that, we'll get quite a big number, 8,205.3 kilopascals. And if we were going to round this, it would round to 2 significant digits, So 8.2 times 10 to the power of 3. So in some questions, you'll have to use specific values for pressure. So remembering these conversion factors is something that you need to be comfortable with. Now what we're going to do is move on to temperature, learn a little bit more about temperature, and then we'll be able to put some of this work into practice. So when we deal with temperature of gas molecules, we have to deal with something called the Kelvin scale. You may already be familiar with the Kelvin scale, but if not, let's go over what it is and what it means. So, first thing, we know from our kinetic molecular theory, temperature is directly related to the kinetic energy of molecules. So, what happens at a lower temperature, the gas molecules are going to slow down, and if the gas is in a container, it's going to press less on the walls of that container. If you have a container with flexible boundaries like a balloon, you'll notice that as the temperature decreases, the volume also decreases, or it shrinks, or that volume of the balloon gets smaller. If you imagine you keep on lowering the temperature and lowering the temperature and lowering the temperature, there would be one point when gas molecules would actually stop moving because they're directly related to kinetic energy. If there's no kinetic energy, they can't move anymore. This particular point when gas molecules stop moving is called absolute zero. You may have heard this in several movies or in other courses, but in terms of chemistry and molecules, the gas molecules stop moving. They have no kinetic energy, and at this point we say is absolute zero. There was a scientist named Jacques Charles, and he figured out a relationship between gas expansion and temperature, so directly relating to kinetic energy and temperature. So he figured out that every time a gas increased by 1 degree Celsius, gases expand by 1 over 273, or 1/273rd of their volume at 0 degrees Celsius. And this formed the basis of the Kelvin scale. So the Kelvin scale is a temperature scale where negative 273 degrees Celsius is 0K, or absolute zero. So this is the scale that we're going to need to use when we're dealing with gas problems if temperature is involved. So what's our conversion factor? At 0 degrees Celsius, it's negative 273 degrees Celsius. This is absolute zero, when the volume of a gas is zero. No motion, doesn't occupy space. Following kinetic molecular theory, it would be zero. How do we convert between absolute zero and our Celsius scale? It's very easy. You're either adding or subtracting. If you want to go from the Kelvin scale to Celsius, you subtract 273. And if you go from Celsius to Kelvin, you add 273. So to practice some conversions, why don't you try these four, and then we'll take a look at the answers. So if we're going from Kelvin to Celsius, we need to subtract 273. So if we do that, we get negative 173 degrees Celsius. Again, 273 minus 273, that's going to be 0 degrees Celsius, or our freezing point. So that's a good one just to keep in check. If we're saying 0 degrees Celsius, freezing point for many things like water, we've got 273K. What if we want to go the other way? Well, we need to add. So 100 plus 273 is 373. What if we have negative? Still works the same way. We add 273. So this would be 73. So you need to know how to convert from Kelvin to Celsius or Celsius to Kelvin, because whenever we deal with problem solving with gases, we have to use the Kelvin scale. Not in degrees Celsius, has to be in Kelvin. So that's something that you'll need to use going forward. So now that we've done some background work on the kinetic molecular theory, how gases behave, we've learned about temperature and pressure, now we're going to try out some calculations with gas laws. So what are some gas laws? We're going to learn about 3 in the lesson today. They're very similar to one another and very easy to work with once you understand what they are. So let's take a look at the first one. The first law is called Boyle's law. Boyle's law relates 2 variables, pressure and volume. So how does it work? It says the volume of a fixed mass of gas varies inversely, which means oppositely, with pressure when the temperature is constant. So, first thing, because this is a little bit tricky when you first read it, temperature constant, this means change in temperature is 0. When we look at the formula for Boyle's law, temperature is not included because the change in temperature is 0 or it's constant. So we don't need to worry about temperature here. So what do we need to think about? Volume is going to vary inversely, which means oppositely, with pressure. So this law is basically saying that if you increase the pressure, the volume will decrease. They're opposite to one another. Or you could say if the pressure decreases, the volume increases. So as one goes up, the other one goes down. The formula itself is P1V1 is equal to P2V2. So your initial pressure and volume is equal to your final pressure and volume when they're multiplied together. You'll notice here that there's no units provided for any of these variables. So you could use any pressure and any volume, but they have to be in the same units. So if you have 2 pressures in your question, both of them have to be in the same units. If you have 2 volumes, they both have to be in the same units. And sometimes the question will want you to do even a conversion. Let's take a look at another law. Next law is called Charles' law. So Charles' law deals with 2 different variables. Charles' law has volume and temperature. So this law says as the volume of a fixed mass of gas varies directly with temperature when the pressure is constant. So volume is going to vary directly with temperature. This time, the pressure is constant. That means change in pressure is 0. We're not going to worry about pressure with this formula. There's one key thing here. It is the temperature here has to be in Kelvin. So what does this mean in terms of the law? So if you see a direct relationship, what that means, as the volume increases, the temperature of the gas will increase. Or as the volume decreases, the temperature will also decrease. That's what a direct relationship means. So what does the actual law look like? It's V1 over T1 is equal to V2 over T2. Initial volume and temperature and final volume and temperature. The temperature for this to be true has to be in Kelvin. So you must always use temperature in Kelvin here for units. But for volume, it's not specifying liters, milliliters. As long as they're both the same, if you have two volume measurements, then you're okay. Now there's one more gas law, and it's Gay-Lussac's law, and it involves the other two variables, pressure and temperature. That's where you get Gay-Lussac's law. So this one says the pressure of a fixed amount of gas is directly related to the temperature when the volume is constant. So here, volume is constant means change in volume is equal to 0. You won't see it anywhere in the formula or with your calculations. But again, what do you see? Temperature scale in Kelvin. So with your temperatures here, make sure you use Kelvin. Here it also says direct relationship decreases. So they're directly related to one another. So now that we've gone through each of the gas laws, let's try out some problems. So have your calculator handy if you don't already, and we'll be able to try out this problem together. So we have a 3.9 liter helium balloon that escapes from a child's hand. It travels from an air pressure of 101.3 kilopascals to 59.6 kilopascals. What is its final volume? So you've probably all seen this or maybe had this happen to you. You're holding a helium balloon, you let go, and it flies away. It's very sad. So here let's write down what we have. We start off with a balloon that has a volume of 3.9. So that means that's our initial or starting volume. It travels from an air pressure of 101.3 to 59.6. So it starts off at a pressure of 101.3. That's P1. And since it's changing to 59.6, that's going to be P2, or our unknown. I take that back. We want to know what the final volume is. So that's our unknown. So when we look at our variables here, V1, P1, P2, and V2, which one of the three laws that we just saw matches with those variables? When we take a look, you should be able to see that Boyle's law is the one that we need. So that's P1 V1 is equal to P2 V2. Now with this formula, we want our unknown to be V2. It's on the right-hand side. So make it easier to do your rearranging. Just flip it around. Mathematically, you're not changing anything. And we want to isolate our V2, which means we need to move P2 away. So V2 stays here. P2 goes from numerator. When we bring it to the other side of the equation, it goes denominator. And now we have our rearranged formula that we can input and solve for. So when we do that, Our pressures, they're both in the same units, which is good. So I'm going to start with P1, 101.3 times my volume, and I'm going to divide it by P2. And then here, I need to round to 3 significant digits. So when I punch this in my calculator, I should get about 6.63 liters. So that's one example of a problem using a gas law. Let's try out another one. So in this problem, we've got a sealed Ziploc bag. It has some air in it, 36.0 milliliters, and it's in the fridge. What happens if you take the bag out and you leave it on the counter? The volume of the bag changes. It now has 39.4 milliliters of air, and we want to use our measurements to try and figure out what the room temperature is. So let's do the same thing. Let's write down our variables. This is our starting volume. And our starting temperature is going to be the fridge at 5 degrees Celsius. Later on, the volume changes, so that's V2. And we want to know what the temperature of the room is. So the final temperature is unknown. So if we're looking at our variables here, we have volume and temperature. Volume and temperature, which law are we dealing with? Is it Boyle's law, Charles' law, or Gay-Lussac's law? Hopefully you see that this is Charles' law. So V1 over T1 is equal to V2 over T2. Now, remember when we're dealing with temperature, we can't use degrees Celsius, so we have to change our 5 degrees Celsius into Kelvin before we can use our formula. So why don't you try that out? How do you convert 5 degrees Celsius into Kelvin? If you remember, going from Celsius to Kelvin, you have to add 273. So when we add 273, you should get 278 Kelvin. Our units of volume are both the same, milliliters and milliliters, so we're okay to start. Now, when we're solving here, we need to solve for T2. A lot of people have trouble rearranging, especially when it comes to putting variables on the bottom. So if you need some help with rearranging, these are some tricks you can do. Just because temperature's on the bottom doesn't mean it can't be on the top. So you could invert your whole formulas here. T1 over V1, T2 over V2. You have to do the same to both sides of your equation. So if you do that, that's great. Now we have our variable, the T2, in the numerator. But then we can use our same trick just to flip your equation side, like we did the last time, T2 over V2, T1 over V1. Again, we still need T2 on its own. But now we can easily see what we need to do. We can rearrange our formula. V2 from the denominator, when it goes to the other side, is going to be in the numerator. So T2 will be T1 times V2 over V1. If you're good with formulas and rearranging, you may not need to do all of these steps. But if you're someone that needs a little bit of extra help, hopefully that helps with how to manipulate this equation. So why don't you go ahead now and try and pause the video and see if you can find out what T2 is. Remember T2 in the question, we want to make sure we convert it back into degrees Celsius. So make sure you do that extra step at the end. So pause and give it a shot, then we'll check your answer. All right, let's take a look. So if we want to find out T2, when we put in all of our information, our temperature, and our two volumes, we get about 304.25 Kelvin. Then to convert it back from Kelvin to Celsius, we need to subtract 273. So to go from here to here, we did our conversion, 273 Kelvin, and we get approximately 31 degrees Celsius for two significant digits. I'm going to give you one more problem, but this time I'm not going to give you any help. So this is the third problem. So I want you to try and pause the video and see if you can answer this question. And when you're ready to check, unpause, and we'll take a look at the answer. So looking at this question, we've got temperatures and pressures. If you're dealing with temperatures and pressures, then you need Gay-Lussac's law. So before we take a look at the question and the actual numerical answers, if we look at our givens, your starting temperature is minus 5 degrees Celsius, which we need in Kelvin, 268. Pressure is in atmospheres. It doesn't say we need a particular unit, so that's fine, 2.18. And our T2 we need to change to Kelvin, so it should be 243. And then we're trying to solve for P2. So again, you have to rearrange your formula before you put in your variables to solve. So this was done similarly to the last question. Now when we take a look and plug in our values, let's see what we get. So when we plug them in, we get 2.18 times 243 Kelvin divided by 268 Kelvin. So that gives us around 1.97 atmospheres. And in this question,